So this is video 6 in our course G05 on antibody analysis, where we're looking at motif identification. So for motif, we're looking at short variable sequences such as of amino acids, RNA, DNA, from which a consensus can be inferred probabilistically because we have a set of sequences with multiple entries at each particular position. Sometimes this calculates what's known as a position weight matrix, PWM, also known as Possum's position-specific scoring matrix, PSSM, or position-specific weight matrix, PSWM. So you can see here what we have is a representation of the information content at each site here as we go along. So you can see there that site 4 is definitely going to be C, and site 12 is going to be G, whereas for site 9, our estimate is more uncertain. So this is this kind of gives us an estimate of how much diversity expect at each site. If we look at a lot of this comes from transcription factor binding sites, TFBS, and MEF2 binding sites are an example of that. So here we have got 14 positions with a set of sequences shown arrayed here across here. So this is sequence 1, and we're looking at each site to see the frequencies of G, A, C, and so on as we go through at each of these 14 sites here. And we do this for all 8 sequences for which we have data. So you can look at the first position, look at the relative probabilities of T and C and G and A and so on, and we do this all the way through. And what we do is we correct the individual frequencies that we observe for each of them by the background frequencies of each of the 4 nucleotides. So we're scaling the relative probability of having a particular allele at these sites. To create a consensus initially, we can look at the nucleotide degeneracy code, say for B and R and M here. We don't have many C's and A's and G's and so on in this instance. And what we can do is count the numbers of the different bases that we see present. So here, for example, we have 3 C's, 2 G's, and 3 T's, and no A's. So that's why we put in this position frequency matrix. By normalizing this, so adjusting it for the background rates of A, C, G, and T across this matrix and log scaling it, we can get a position weight matrix, which we see here. So you can see there, A is rarer, C is more common, T is somewhat common, and G is in between. So we've scaled it by the random chance of having each of these nucleotides. So where A is unlikely, C is most likely, then T, then G, but there's not much differences. Whereas if we look at site 4 here, it's pretty clear-cut that it's going to be C because that's much more positive than the other 3. And therefore we can convert that position weight matrix into a sequence logo, as we can see here. So that's the site 4 corresponding to this big C here, whereas at site 1, the probabilities of getting T, C, and G are comparatively similar. So that's our position weight matrix and our sequence logo created there from this short motif that we're trying to infer. So we can think about this more precisely. So if we're thinking about this position weight matrix, we're looking at the frequency of each base at each site, and we can have this formula here for that. So where we have F, which is looking to count data, and then we may have a pseudo count function inside there if we have many, let's say 0 values there. We have our number of sites there, and then we sum across an approximation for our pseudo count function as well. So we scale this by the background expector rate for each base to get the position weight matrix value, which is log 2 scaled. So that's why if we had looked at site 1 there, we have relatively equal numbers of T and C, and yet when we put them into the position weight matrix, you see that C is slightly more common than T scaled for the background rate. And we can also get the information content from this formula, again, getting the summing across each of the bases for a particular site and getting the log 2 scaled, getting the log 2 scale function of that as well. And then we just have an offset to prevent 0 values. The tools that we use for this come from the meme suite. So MEME stands for multiple expectation maximization for motif elicitation. So that allows the inference of the most likely sequences at a particular motif of interest. A related tool that we use is called GLAM2, Gapped Local Alignment of Motifs version 2. And this is more effective for discontinuous motifs and therefore is better for antibodies. It can identify linear motif sequences and the conformational properties. So GLAM2 is nicer because it allows looking at gapped motifs where um, the data we have that may vary out. It allows indels to be present and uses a simulated annealing problem to kind of gradually tweak temperatures across the data set that is present to by making random changes to optimize the most likely arrangement of interest. And what it's getting is an alignment of the immunoglobulin segments, and that's based on a particular alignment algorithm that kind of uses principles from maximum parsimony in there. So it starts with a random alignment initially, and then makes many small changes, and then gradually realigns just to estimate the net effects. It reruns it at least 10 times. You can change that to be a different frequency if of interest, and it looks to see which motif is the best scoring option, and it can be run for longer if the score is not high. Notably, if the numbers of input sequences is very large, the optimal alignment may not be found necessarily in terms of the number of runs, but that may not be desired necessarily once the most likely solution is clear. So that kind of finishes this kind of theory part before we talk about the practical part of how to implement MEME and GLAM2 in the demonstration videos.